So now we're going to learn about some probability rules. So make sure you read these learning targets. I'm going to move on. So we have the sample space, S is the name of the sample space. We can use any sort of name. Of a chance process is the set of all possible outcomes. So if we were to flip a coin, our sample space would be heads, tails. That's everything that's possible. A probability model is a description of some chance process that consists of two parts, a sample space S and a probability for each outcome. So this would be part of our probability model, but we would also need the probabilities. We have X is a heads or a tails. The probability of a heads would be 50%, and the probability of a tails would be 50%. So between these two things, we have a probability model. An event is any collection of outcomes from some chance process. That is, an event is a subset of the sample space. Events are usually designed by capital letters like A, B, and C, and so on. So if we said A is rolling one heads, then we could say the probability of event A is 0.5. So give a probability model for rolling two dice. Well, a lot of things can happen. If we roll a six-sided die, because it doesn't specify, we're just going to assume, we could get 1 and then a 1. We could roll our dice, we could get a 1 and a 2, listing everything that's possible. A 1, a 3, a 1, a 4, 1 and a 5, and a 1 and a 6. Then if I roll a 2 with my first dice, then I can roll a 1 with the second one. I could roll a 2 with the second one, 2 and 3, 2 and 4, 2 and 5, 2 and 6. And I'm going to continue to list these out. Then we have X. X is representing what the sum of those two die are. Well, if we roll a 1 plus 1, we would get a 2. So that happened only one time, because 1 plus 2 is 3. Everything else is going to be bigger. So this happened one time out of all 36. There's 36 different things that could happen, right? 6 by 6. To roll a 3, you would get a 1 and a 2 and a 2 and a 1. So that is 2 out of 36. Then we see how many times we can add up till 4. Well, 3 plus 1 is 4, 2 and 2 is 4, 1 and 3 is 4, so there's 3 out of 36. Then we have 5. Well, 4 and 1, 3 and 2, 2 and 3, 1 and 4. There's 4 different ways out of 36. And if we see the pattern, then we can keep going. Then at 8 is where it starts to go down. If we look the other way, at 12, 6 plus 6 is 12, but everything else is smaller. So this is 1 out of 36. And then with the 11s, only 5 and 6, so 2 out of 36. Use the probability model to find the following probabilities. Well, what's the probability that we roll a 3? Well, it's 2 out of 36. That was easy. The probability that the sum is a 3 or a 6. Well, the probability that we get a 3 is 2 out of 36. And the probability that we get 6 is 5 out of 36. Well, we just add those together because we want either of those to happen. So we have 7 out of 36. The probability that we get a prime, well, prime numbers are 2 plus the probability if we get a 3, then 5, 7, and 11. Those are all my prime numbers. So the probability I get a 2 is 1, then plus 2 more, so 3 plus 5 is 7, plus 6. 7 plus 6 is 13, and plus 11, so 15 out of 36. So basic rules of probability, so we're going to do some more. A standard deck of playing cards with jokers removed consists of 52 cards and 4 suits: clubs, diamonds, hearts, and spades. Each suit has 13 cards with denominations ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. The jack, queen, and king are referred to as face cards. Imagine that we shuffle the deck thoroughly and deal 1. Let's define events A as getting a face card and B getting a heart. What's the probability that we get a face card? Well, there's a jack, queen, and a king of each suit. So there are 3 for each suit, so times 4. So there's 12 face cards out of all of those 52 cards in the deck. Probability of A and B means that we're looking for the probability that we get a face card and that face card is a heart. Then the probability of A and B, well, the probability of getting a face card and that face card is a heart. Well, there's only 3 face cards that are hearts out of all 52 cards. But the probability that it's A or B is a little different. This is the probability that you get a face card or you get a heart. Well, there are 12 face cards out of 52, and there are 13 hearts out of 52. But I counted a couple of those things twice, because a couple of those face cards are also hearts. Exactly 3 of them, to be honest. So we're going to take those 3 out that I counted twice. Right? The King of Hearts, the Queen of Hearts, and the Jack of Hearts were in both this list and this list. So I want to subtract them away. So this probability is 22 out of 52. And then the probability that we do not get a face card is the opposite of the probability that we do get a face card. So if you think about it, we have the ace through 10, and we could multiply those times 4, so there's 40 out of 52. The other way we could have thought about this is it's the opposite. We could say, well, we have all of them minus the 12 out of 52 for the face cards. So what this would be is also the same, because we would have 52 out of 52 minus 12, so that's 40 out of 52. For any event A, the probability is between 0 and 1. You can't have a negative probability, and you can't have a probability that's more than 1, aka more than 100%. That doesn't make sense. If S is the sample space in a probability model, the probability of S is 1. In other words, all the probabilities add up to 1.
In the sample space.
Then we have our complement rule. The probability of A complement is 1 minus A. So this not A is the same thing as A complement. And I already showed you a little bit. It's that 1 minus. It's like thinking about things that are the opposite. The addition rule is this probability of A or B. Now I didn't show you the symbols yet. So let's go through and learn these symbols. We have probability of A and B. Remember, those are the same thing happening at the same time. We use this symbol, which is called intersection, because it means both happening at the same time. this probability of A or B, A union B, this is union. It's just the probability of both of them happening, not necessarily at the same time. So it's like in either is really a better word. So we have union and intersection. I'm going to use those for the rest of the time. So we have the probability of A or B. And this is the probability of A plus the probability of B. But remember, some of those get counted twice, because remember when A and B happen at the same time? With this example, we had a face card and we had a heart. Well, there are some face cards that are hearts, so you counted them in both things, so we have to subtract off the ones we counted twice. So in the symbols, we say minus the probability that both are happening, A and B, that intersect B. Two events are mutually exclusive. Another word for mutually exclusive is disjoint if they have no outcomes in common and so can never occur together. How would this change the addition rule? Well, we have the probability that you have a 2 or you have the probability that you would have a face. So using the general addition rule, we would say this is the probability that we would have a 2 plus the probability that we would have a face card minus the probability that you could have a 2 and a face card at the same time. A 2 and a face card are different. You can't have both at the same time, so the probability of both happening is 0. But the probability of a 2 is 4 out of 52, and the probability you get a face card is 12 out of 52, but we would just say minus 0. So we don't need this subtraction for mutually exclusive or disjoint events. We don't really use disjoint that much. You'll see it occasionally, but mutually exclusive is the key word. So if they can't occur together, the addition rule would just be the probability of A or B equals the probability of A plus the probability of B, because you don't have them counted twice. Distance learning courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking a distance learning course for credit and record the student's age. Here is the probability model. So show that this is a legitimate probability model. So first of all probabilities are between 0 and 1. And 2, we need to show that all probabilities add up to 1. So 0.57 plus 0.17 plus 0.14 plus 0.12 add up to 1. And they do. Find the probability that the chosen student is not in the traditional college age group. So what we could do is we have the probability that they're in the age group. Well, that is 0.57, but we want not in that age group, so the opposite. So we want the complement of this. So we want 1 minus 0.57, which is 0.43. Students in a college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on 2 variables, gender and whether the student had a pierced ear. For all 178 people in the class, the two-way table below displays the data. So suppose we choose a student from the class at random, find the probability that the student has pierced ears. Well, we've done this before, so let's call pierced ears P. So the probability of P. So what pierced ears is 103 out of 178. Then we want to know the probability that they are male with pierced ears. So instead of saying this is the probability that they are male and they have pierced ears, okay, that intersect. So this is They are male and have pierced ears, so 19 out of 178. We want to know the probability that they're male or have pierced ears. Well, we have the probability that they're male or union have pierced ears. This is the probability that they're male plus the probability that they have pierced ears minus the probability of both male and have pierced ears. So if they're male, the probability that they're male is 90 out of 178 plus the probability that they have pierced ears is 103 out of 178 minus the probability that they have both male and have pierced ears, so that 19 out of 178. Now remember why we have to subtract this. If we count the number of people with pierced ears, well, it counts those 19 males and the 84 females. If we're counting the amount of males, we're counting the 19 who have pierced ears and the 71 who do not have pierced ears. So we counted this 19 twice. So that means we need to subtract it off because we counted it too many times. So 90 plus 103 minus 19 is 174 out of 178. Now this makes sense because there are a lot of people that are male and a lot of people who have pierced ears, but there's only 4 people who do not have pierced ears and are not male at the same time. Those 4 people are the ones that are not in it at all, and that should make some sense. If we look at a Venn diagram and we make a Venn diagram of this, we can use the table above. So if we have probability that they're male and the probability that they have pierced ears, well, the probability that they're both is 19. The total number of males is 90, but if we take those 19 away, we have 71. So this is 71 males that do not have pierced ears because it's not in that circle. But then we want to know the number who have pierced ears who are not male. There are 103 people that have pierced ears, but 84 of them are not male. So 84 belongs in this one. And then outside of all of this are those 4 people that are not male and do not have pierced ears. So that's the not. That's the both, that's the not. So I think that this Venn diagram makes it kind of easy to see. So here are some examples of the Venn diagram, and then I want to come back and show you how this works. So this is A, the blanks, and then this is not A, everything outside of the event A. This is event A and event B, but they do not overlap at all. This is when we have the mutually exclusive, or disjoint is the other word that we use, events. This is A intersect B, or A and B. So this means both have to be happening at the same time. You see that overlap? And then this is the A or B. So it's either in A or in B or in both. And there's a nice little picture of that. So here's another picture where we have event A and we have event B. And that overlap, you can see, is counted twice. You can see that middle purple section we counted in A and we counted in B. So if we add those 2 events together, we need to subtract off where that happens in that same place, that and. This middle section was counted twice. So there's a nice visual representation of why we subtract. In an apartment complex, 40% of residents read USA Today. Only 25% read the New York Times. 5% of residents read both papers. Suppose we select a resident in the apartment complex at random and record which of the 2 papers the person reads. Make a two-way table that displays the sample space of this chance process. So we have USA Today, and we have the New York Times. So they either read this, yes or no, or they read this, yes or no. Well, 40% of residents read USA Today, so 0.4, I'll say 40, read USA Today, and remember this is 100%. 25% read the New York Times, so 0.25. 5% read both, so they read USA Today and the New York Times, so 0.05. From here, I can get the whole rest of this chart. So 5% read both, then that means only 0.35 reads USA Today, but not New York Times. And then this way, I could say 0.2 or 0.20 read New York Times, but not USA Today. Then I know that 0.25 plus 0.75 adds up to 100%, and 0.4 and 0.6 add up to 100%. So that means that this is 40% of people do not read either. Construct a Venn diagram to represent the outcomes of this chance process. So blue is going to be USA, and red's going to be New York Times. So the amount that reads both is 0.05. So the amount that reads USA Today but not New York Times, so yes to USA Today but no to New York Times, is 0.35. Then we want to say yes to New York Times but no to USA Today, so this is 0.2. And that should make sense because this whole circle adds up to 0.25 and this whole circle adds up to 0.4. And then we have outside the circle 0.4 for people who don't read either newspaper. Find the probability that the person reads at least one of the two papers. So this is the probability of USA or New York Times. If we use our formula, we have the probability of USA plus probability of New York Times minus the probability of both, USA and New York Times. So this is the probability of USA Today is 0.4 plus the probability of New York Times is 0.25 minus the probability of both, 0.05. Well, this is one of those cases where using this Venn diagram might actually be a little more helpful, as we would just add 0.35 plus 0.05 plus 0.20, and that would give us 0.6. From here, you'll see the same thing. This is 0.65 minus 0.05, 0.6. So it doesn't matter how you do either way as long as you know what you're doing. The formulas you're going to need to know, they're very helpful, but using the pictures and the two-way table helps a lot as well. We want to find the probability that the person doesn't read either paper. Well, we know from here that it's 0.4, but let's use some formulas. We should say the probability we want the complement that they would read either of these papers, right? This is them reading either paper. We want the opposite of that because they don't read either paper. So this is 1 minus 0.6, which is 0.4. And that matches from our Venn diagram and from our two-way table.